Welcome to this NPTEL lecture on principles and techniques of modern radar system. We were discussing FMCW radar in previous class. We have seen an FMCW radar with triangular modulation, that up ramp and down ramp both are there. Now, we said that can we have a sinusoidal frequency modulated CW radar? Yes, the answer is yes. If you are detecting a single target and if the target is at short range, then you can use. So, that analytic derivation we will do today. So, let the transmitted frequency, transmitted signal voltage, that is something you give A T amplitude. The amplitude does not matter here, because everything will depend on the frequency. So, sine I can write, I have a sinusoidal modulator. So, sine 2 pi f naught t, this expression I think you know that, because in your analog modulation classes the frequency modulated wave is like this, sine omega naught t plus delta f by 2 fm sine 2 pi fm t. So, it is modulating, the frequency is getting modulated with a modulating frequency fm. Okay. This expression is known. So, let the transmitter is using that transmitter, that means simply an FM transmitter you are using. And what is the received signal? So, I know received signal will be delayed by a time delta t. So, I will do that. The amplitude I am writing something else AR, then sine 2 pi f naught t minus delta t plus sine 2 pi f m t minus delta t. Delta t is the transit time, and lest we forget what is delta t. Delta t is nothing but 2 r by c. Now, I have assumed, because we have seen that generally these FMCW radars are used for detecting short range targets. So, short range. So, what is the meaning of short range? That means delta t. So, short range means delta t is much smaller than 1 by f m. That means the modulating frequency compared to that, it is much smaller. So, sine of pi f m delta t, when I am writing this, actually that means can I write that f m delta t, if I multiply with pi also, that also is much smaller than 1. So, we know that sin theta is equal to theta for small arguments. So, can I write this equal to pi f m delta t, and so this expression delta f by 2 f m, this what will happen to this expression? Can I write now that delta f by f m, then sine pi f m delta t, that will be then pi delta f delta t. So, what will be now? I know V t, I know V r. In V r, I will have to make this simplification, and then I know that the receiver of this radar will heterodyne that and produce a beat voltage. So, what is VB expression? I can say sum multiplier AT AR, then you see it is basically sine. So, I know that when it mixes, the basically the argument of this both of the sine function. So, they will be difference. So, can I write 2 pi f naught delta t plus pi delta f delta t. This you can do, just you do on your own. I am just helping you with the major step. So, it is sine minus sine. So, cos terms will come. So, sine k v t sine plus del, or let me give another step, so that you later do not have problem, plus delta f by f m cos, that 2 is going because there are cos 2 sine terms. So, there is a 2 there. So, cos 2 pi f m t minus delta t into sine pi f m delta t. This is the expression that these two, from here it comes. Then you put these simplifications, and so with that simplification you can now write that this is k a t a r sine 2 pi f naught delta t plus pi delta f delta t cos 2 pi f m t minus pi f m delta t. I think there should be a third bracket. Okay. Now, this is the bit signal. So, what is the bit frequency? So, you say bit frequency is this argument that should be differentiated with time, and that will give us the bit frequency, or that will actually give us the angular bit frequency. We will have to divide that by a. So, I can from here I can write that what is f b. F b is, you do it, this is a, you see that only this term is time dependent, these are all invariant to time. So, they are going to the phase of the thing, only this term. So, cos, if I differentiate, there will be a minus sign due to that from angular frequency to this, and then I have this pi delta f delta t, then 2 pi f m, then sine 2 pi f m t minus pi f m delta t. Okay. So, this again I can simplify, it will come to pi delta f delta t Fm sin 2 pi Fm t minus pi Fm delta t plus, I am writing pi, that minus sign I am absorbing in the phase, plus pi. Okay. Now, this is where, so you see that sinusoidally this frequency is changing with time. So, bit frequency is not constant of time, but I can measure the average, I can put an averaging meter. So, let me see what will happen if I average that I am calling FB average. So, that will be, we know how to take average. So, over the one half cycle I will make that average, because we know that up frequency and down frequency are always changed. So, over a half modulation period we will do that. That means 1 by 2 Fm, then 0 to 1 by 2 Fm, then Fb dt. So, pi delta f delta t Fm sin 2 pi Fm t minus pi Fm delta t plus pi dt. This will be my average thing. So, if you do this, then you will see that the sine integration, that will give you a cos, then you take these two limits, and that will give you 2 delta f Fm delta t cos of pi Fm delta t. Now, we already have seen that Fm delta t, this their product, that is much less than 1. So, we can say that cos pi Fm delta t, this thing will, under that assumption, that short range. So, this is becoming 1. Okay. So, this then approximately becomes that 2 delta f Fm into delta t. Okay. Now, already you see these terms delta f, Fm, their product we have seen, because f dashed, that was that delta f by 1 by Fm. So, delta f Fm, and from there we have related to r. So, we can immediately bring r here. So, this, or let me write here that, remember this, that already we have found that Fr is 4r Fm delta f by c. So, if I put that here, then I can write that, and also we know the value of delta t, that also let me write by some other color. We know these two things, that delta t is always, we know 2r by c. So, if we put them here, then we get this FB average, that will be become, you will see that, so what will happen, Fr. You put these two, it will become Fr. So, it also is directly giving you Fr. So, if you make bit average, that will give you a Fr. Now, Here we have assumed a stationary target case, but if you do the derivation for Doppler also, it will be. That means, even if you use a sinusoidal thing, only thing you need to put an extra averaging meter. Actually, it can be generally shown that any reasonable shape modulation waveform can be used to measure range if average bit frequency is measured. Only thing you need in that a positive cycle and a symmetric negative cycle. So, various other types of modulators are also used. So, also Doppler shift, if it is present, it will be there. So, upsweep and downsweep time, that should be equal, that means the symmetry that should be there. Now, major application of this type of FMCW radar is on board all the radar, all the aircrafts, they measure they have an altimeter by which they measure their height from the ground. When you fly, etc., you will see that always on the go nowadays modern aircrafts, they show that now it is at so and so height. So, that time actually the ground is the target, it is sending a continuous wave signal, it is frequency modulating and receiving the thing, then it is doing this business and going there. So, also you see that RCS of the ground is a good scatterer of thing at microwave frequency. Obviously, at various frequencies the RCS of ground is different, but at microwave frequencies these radars operate. So, it has a good RCS. So, also the range is short. So, with a low transmission power also you can get reasonably good return for having a simple radio detector. The antenna also need not have high gain, a low gain antenna will do. Usually nowadays even patch antenna or a simple dipole antenna or monopole antenna, that can be done. Now, also the Doppler is small because radial velocity of the target with respect to that means the change of the velocity of the radar, that is not much. So, Doppler is neglected. So, it assumed a moving stationary target. Also, here there are no clutters because ground here, generally ground is a good source of clutter, but here ground is the target. So, no question of much clutter. Now, in industry this CW radar is heavily used. Suppose in a blast furnace, the molten iron in blast furnace, what is the distance? So, distance measurement of molten iron in blast furnace, I said that if that distance is not known, then actually at what time you will have to take it out, otherwise the molten iron will blow the blast furnace. So, by sending this you find out that how much molten in there, what is the distance, has it come to the point where we will have to take it out. So, all this measurement is done. Now, in the aircraft the detection etc. So, in the Hawk air defense, that means that time in the detecting an aircraft also in 50s this FMCW radar was used, because that time the pulse radar was not good, but nowadays pulse radar is not used much. And another problem with this for detection of pulse radar, for detection of aircraft, that time the transmitter is high power, and so the receiver and transmitter then needs to have large amount of separation for FMCW. In pulse radar that problem is not there, that is why pulse radar has become more compact, and nowadays it can give you much more range compared to FMCW. So, that is used. So, we will see the block diagram of this FMCW radar next, because so block diagram is, you have a modulator, then that modulator is feeding a FM transmitter, and then that is put to an antenna. So, Then, so I will say that transmit antenna, this is your received antenna. So, the signal is coming here, then that is put to an mixer, RF mixer, and in that RF mixer from this one also a reference signal is brought. So, mixer is fed with the received echo and this reference signal, then you know the bit frequency is already produced, then you need an amplifier, then there will be a limiter, and then there is a, because amplitude you are not interested. So, you put a limiter, put to a frequency counter, it will make its job easier, frequency counter, and that will go to an indicator. So, it will tell you what is the range, because indicator will have that mapping, and so I will this. So, this is the block diagram of a FMCW radar. Okay. Now, we will see that as I said, this is the FMCW. Now, range measurement also can be done with CW radar by not doing frequency modulation, but doing something in frequency, that is called double frequency radar. That is an alternate principle. So, I will discuss that. Why? Because in simpler versions that will also do, instead of having a modulator, because modulator is a bit more complex. So, you can have, now here actually this, so I will start that, sorry. Double frequency CW radar. You see that till now we are discussing that radar is measuring the range by measuring the time. Now, here we will not measure time, we will use another measuring thing, that is phase. You know, suppose I have a signal, so that signal is coming back. So, it is covered the extra distance. So, that you know that any wave, if it goes, so there is a space change, because we say that phase constant into the distance traversed. So, if it traverses toward distance, there will be correspondingly that beta into that 2r, that type of phase change. So, between the transmitted and received signal, if I can measure that phase change, then also I have the range information, because that space phase is also proportional to the range. So, this can be done, but there are two problems. One is that how we will separate the transmitted signal and received signal in a CW radar, because you do not know which one you transmitted and which one you because you are continuously sending. So, you are also after the initial delay, you are also continuously receiving. So, how will you separate? Agreed. But if you can do that, let us say somehow I can put some mark on the signal, so that I know there that what is the that corresponding to that mark. So, what is the transmitted signal, what is the received signals, what is the transmitted signals phase, what is the received signal phase, then I can do. Another thing is that phase measurement. So, two problems. One, I said that how you, so first thing I will say that this is a phase measurement we are doing for detecting range, phase measurement for range detection. number 1 in this principle. Two problems. One, I said that how to separate transmitted and received signal phase. Which one is transmitted? Now, that problem will solve by putting two frequencies, that will show. But there is another problem, that phase measurement now has an ambiguity, because you know that phase is a periodic function, time is not a periodic function. So, I can measure any time, but phase after 2 pi, actually if I measure 3 pi, that is basically 1 pi, and all the values they are that thing. So, phase measurement should be restricted from for a 2 pi duration. So, if range is proportional to phase, range will also get restricted, and that is true. We will see that there is only very few length, actually it is almost some lambda by 2 or something. So, that is not useful, but we will see that how people have overcome these two problems. So, I will say that ambiguity of phase, ambiguity of phase measurement beyond 2 pi. Achha. So, these two we will see, but let us say that if I can measure phase, then how I can measure range? You see, what is the phase difference? Phase difference between transmitted and received signal, let that be delta phi. If that is there, and we know from our knowledge of electromagnetic theory that how much this will be, it is nothing but, can I say 2 omega naught R naught. R naught is a range by C. Again I am assuming a fixed target, not a moving target. So, this is nothing but 4 pi f naught R naught by C. So, I can have a phase detector, I can do, but then this portion I need to restrict, or this whole thing I need to restrict delta phi should not be more than 2 pi. So, my condition is delta phi should be less than equal to 2 pi to have this ambiguity problem, and that means you see that if you put it here, what is our unambiguous range measurement maximum, that turns out to be lambda by 2, as I was saying. Now, in microwave region, then it is not useful. But these two problems, that how to separate transmit or how to put marks on a CW signal, and this much that though phase can be measured, but this is a thing, these two can be circumvented by transmitting two signals differing only in frequency very slightly, let us say F1 and F2. So, that is the double frequency signals beauty. So, let us say that we are transmitting V1 t, there is a transmitted signal sin 2 pi F1 t plus phi 1, and V2 t we are transmitting. Deliberately I am not writing amplitudes, because ultimately I will be mixing or detecting phases, that also is a mixer. So, not a problem. plus phi 2. Let us say phi 1 and phi 2 are the initial phases. Now, please remember that at the basic principles last we have derived that, or for a CW radar we have derived that for a moving target, this I will write by this pink one, we have already derived an expression for the moving target, received signal from a moving target, that I am writing that received signal VR from a moving target case, we have derived that was sin omega naught plus minus omega dt. Please, this you refer, we have already derived that deliberately. That time I said that keep it, later we will use it, now we will use it. This was the expression that we have derived earlier. So, we are sending the transmitter is sending two such signals F1 and F2. So, we can easily write what will be V1R, that sin, sorry, let me use this black, sin 2 pi F1 plus minus Fd1 t minus 4 pi F1 R naught by C minus plus 2 pi Fd1 t naught plus phi 1. T naught is nothing but the initial time, and V2R, similarly I can write sin 2 pi F2 plus minus Fd2 t minus 4 pi F2 R naught by C minus plus 2 pi Fd2 t naught plus phi 2. Okay. R naught, that time we define that it is the range at time t is equal to t naught. Now, we are saying that transmitter is sending F1, F2, F1 and F2 are close by, F1 is almost equal to F2, but definitely different, and let us assume that F2 is F1 plus delta F, where this delta F is much smaller than F1. So, with this is a very important thing, that basically two nearby frequencies. So, this will make Fd1 almost equal to Fd2, and let us call that value Fd. Now, the receiver will get this signal, that heterodynamic with the corresponding transmitted signal separately. So, Doppler signal it extract. So, it is V1 or bit frequency it extract. So, V1D, that voltage signal will be cos, if you do that, sin minus sin. So, we will get cos plus minus 2 pi Fdt minus 4 pi F1 R naught by C minus plus 2 pi Fd t naught, and V2D is cos, again plus minus 2 pi Fdt minus 4 pi F2 R naught by C minus plus 2 pi Fd t naught. So, these two signals we find the phase. So, phase is what? That 4 pi F2 minus F1 R naught by C. So, it is 4 pi delta F R naught by C. So, from here I can, you see, easily find out what is my range. R naught is C delta phi by 4 pi delta f. Delta f I know because I have transmitted. So, you see that now what is my unambiguous range? R, again if I put the restriction, it is less than 2 pi, R unambiguous, that is C by 2 delta f. So, you see, instead of lambda by 2, just by making two different frequency, I can do that. I can do the measurement also. So, this is a very simple technique, and by what factor actually I have changed the unambiguous thing. This is a practical thing. So, the factor of improvement or improvement factor of range is f naught by delta f. Now, or f naught means actually f 1. So, delta f is very small. So, by a large factor we can do that. So, let us say that this is f 1 or f 2 whatever. So, what is my, suppose I have a f 1 3 gigahertz. Let us say the target velocity v naught is 600 kilometer per hour. Now, immediately I can find out what is the maximum, this is the maximum velocity v naught max, the target's maximum velocity. So, f d max, that you have formulas, by that you can find out that it will come out to be 3.33 kilohertz. And so, if you put that, the R unambiguous, that will become, you will see 45 kilometer. So, this is usable. So, actually you see that 2 frequency means you are putting the mark in the spectrum. So, the two problems I said, the first problem is solved here, and second problem, you see this technique has made this thing, because it has changed the whole spectrum, and by which the unambiguous range also changed. So, this phase detector can be used. Let me just briefly give its block diagram, that it will have a, suppose a f 1 oscillator. From that also there will be a delta f oscillator, and that delta f oscillator will be put to a mixer, and so this output will be f 2, and both of these are put to a summer, and then there is a power amplifier, and then it is transmitted to the antenna. So, this is the transmitter side, then in the receiver side you will have the receiving antenna that will take it, then they will put the signal to two mixers. Mixer, at that time we are saying, so you can say mixer 1, mixer 2. Okay. So, then who will give, suppose this mixer 1. So, from this you will take a path you are giving. So, these two, the output will come. So, this you are giving. So, mixer 1, that will put to a Doppler amplifier, and that is put to a phase detector. Similarly, this mixer 2, this signal is put, receive signal, and from this f 2 you take this. So, this output again put to a Doppler amplifier and put to this phase detector. This is giving you the delta phi, and then you have a range indicator. You see, it is a simple circuit. Only thing is these two oscillators are only thing. So, this is your double frequency CW radar. And only thing is, I think all of you know phase detector in phase modulation, many times you have done. Basically, phase detector is what? Analog multiplier circuit. So, you have a multiplier, you give, let us say, A1 cos omega t, cos omega 1 t, you give A2 cos omega 2 t plus delta phi. So, it will give you alpha, some constant I am assuming, A1 A2 by 2 cos omega 1 plus omega 2 t plus delta phi plus alpha A1 A2 by 2 cos omega 1 minus omega 2 t minus delta phi. So, you can, after this you put a filter. So, that will remove the high frequency. Also, if omega and omega 2 are nearby. So, basically, so that means this term is going out by a filter, by a filtering you can do that, and then this term is very nearby. So, this is almost 1, and so that means you can put an phase lock loop in the circuit, and that phase lock loop. So, if we call this signal as y t, so phase lock loop, you know that this is a cosine function. So, this is your pi by 2, this is your minus pi by 2. So, near this you have a linear region, and you know that this y t, that can be approximately written in the linear region as alpha A1 A2 by 2. Then instead of this cos, I can write pi near that region. If I can lock it in this linear region, pi by 2 minus delta phi. So, you see that this is a bias, but this. So, y t is proportional to delta phi. So, you can easily in this region, if you can lock, after this filter you put an phase lock, and then your with delta phi the signal. So, you can easily find range. The more precise you are in this measurement, more precise will be your range indicator. So, this circuit is simple. This is the phase detector circuit. Just for your refreshing, I have given you this. So, this is a simple circuit, you can make it, and that makes a very simple CW radar. So, with this we are finishing CW radar. Any one of you I encourage, please buy these components and make the radar. These are simple components nowadays available very cheap. From your pocket you can buy that, and you can make your own radars. Only do not transmit with much power, then you may caught by the spectrum regulation agency, but with a low power you can no problem, 1 milliwatt etc., that is not a problem. Okay. So, do that. This is a simple radar, enjoy this radar. In the next class, we will go to the radar which you cannot make from your own pocket. Those are pulse radars. We will start seeing that. Thank you.